So, where did we end? So, no, well, more than where did we end? We first defined anything that satisfies any lambda that satisfies this equation to be a general homogeneous Lorentz transformation. Because if we define it by this equation, what happens? What is the advantage of defining lambda like this? Then this quantity is preserved in the sense if I don't transform the vectors or if I transform the vectors, the inner product remains the same. So it's like a real inner product. Okay? And then we said, well, then we specialized. What did we specialize? We wanted lambda to belong to what? A special subset, determinant 1, and something that preserves time. And we talked about, but clearly, translations belong, translations is identity lambda, but rotations belong into it, and boost belongs into it. We talked about boost just being in the x-axis, but we know that there's y-axis, z-axis, and any other axis in between that you can do. Again, let's restrict ourselves to matrices. Is there anything else? Is there some other kind of matrix hiding in there? That is what we will address today. The answer, of course, is no. Okay? So, there's one problem I want to state, which will be used very soon. This is 2.12. I've uploaded the chapter 2 notes, so they're correct as they're on the website. Suppose you have a Lorentz transformation, and I wrote it in this order: A, B, C, D. Suppose you have a Lorentz transformation of this type. Now, when you look at this, what does this remind you of?
Looks like a rotation.
Does it look like a rotation matrix?
Yeah.
Looks like a boost.
Yes.
Yeah. So suppose you have that is the problem. Suppose you have a lambda like this, and lambda belongs to the proper orthogonal Lorentz inhomogeneous Lorentz transformation, or Lorentz group for short. Then the problem says, then show that lambda is a boost along the x-axis. Yeah, so it would be more difficult than simplest problem. If it takes this form, and if the determinant is 1, and if A is greater than 0, then it has to be a boost. And it's important for you to verify it. It's just algebra, but it's important. But then, it's a boost. Any question about the problem itself? I'm going to write the theorem and prove it. I will not ask you such a proof. I will be testing you on the proof, but I totally recommend that you study it, and we'll try to build a project around constructing an example for a proof so that it drives the point home. No, at least follow the arguments of the proof. And then you have it in your notes. Whenever you need to, you can consult it. Okay. I think it's a beautiful, beautiful theorem. It's not complicated at all. I say that after studying. struggling with it. You know, physics and math, as Richard Feynman used to joke, that mathematicians prove only trivial things. What he meant by that was mathematicians would sit weeks upon weeks, month upon month, struggle on a problem, and finally they solve the problem, and then they say, well, it's trivial, because they have solved it. So, but this is in the category of difficult theorems. I know this is an introductory course, but nonetheless, it's not a difficult proof. This is theorem 2.11. So, suppose, I'm not going to write the whole theorem, as always. Suppose lambda belongs to the Lorentz group. Then, lambda equals, I'll have to explain every single term and how I wrote it. R1, lambda b, beta 0, R2, where R1 and R2 are rotations. No, not rotations. Rotations. And lambda b beta 0 is a boost along the x-axis. X-axis with beta equals beta 0. That's the theorem. Look at what it's saying and how nice the theorem is. First of all, it says let lambda belong to this. That means lambda is any such matrix that satisfies this equation. Determinant of lambda is 1, and lambda 0, 0 is greater than or equal to 1. It's positive, right? Then, lambda, any lambda can be written as a product of 3 matrices. 2 of them are rotation, and 1 of them is a boost along the x-axis. So if this is true, in the set of all matrices that is part of the Lorentz group, can there be anything outside of rotations and boosts? No, that's what the theorem is saying. Yes, Kate?
Oh, no, sorry.
Yeah, that's what it's saying. It's made up of only rotations and boosts. And they were very nice. If you pick your R1 and R2 carefully, it's not rotation about any axis, but about which axis? You can rotate it so that you're only boosting along the x-axis. Then you do another rotation to get back to the other, where the axis was set.
Oh, so you're just changing it so you can boost along the x-axis
Yeah,
and then rotate it back?
Yeah,
oh.
Curiously enough, a good homework problem would be, which I had not included, I could have given you a boost along the y-axis. And I could then say, find these rotations so that it's a boost along x-axis in the middle.
Wait, so is R1 just the inverse of R2 then?
No, we constructed it explicitly. It's not complicated, like I said. It's kind of a neat result. You expect it to be complicated, but we have built all the tools. So is the statement clear? Is the importance clear? Yeah. So when we know the importance of it, yeah, we're ready to go to the proof. So proof. If lambda 1, 0 equals lambda 2, 0 equals lambda 3, 0, then there's nothing to prove. Why is that?
There is no proof. It's just, they must equal 1. They must line up.
No, suppose these guys are 0. I'm going to erase this part. Suppose lambda is such that I have lambda 0, 0, then I have 0, 0, 0, then I have stuff on this side. But it satisfies this equation.
Yeah.
Then I have nothing to prove due to a problem that we have seen before.
There's no length. There's no, you're not multiplying the length, right?
What problem is it? Is that the problem we just discussed? I can't find. Since I can't find it, let me do the favorite things of when I can't find something, which is what? Oh, no. No, look at problem 2.9. In this case, first of all, I would have that lambda 0, 0 squared equals 1 plus lambda 1, what was that result before? Yeah. K equals 1 to 3 lambda 0 k squared. Correct? With this we proved, this is theorem 2.9. Correct? Yeah. But over here, what's true? These guys are? These guys are 0. That means lambda 0 squared equals 1. Which means lambda 0 is plus or minus 1. But this belongs to orthogonals. So that
The indices?
it's true both ways.
Both ways.
Yeah. If you look at the proof. So that means this has to be plus 1 because of this guy.
Since it's
So-
orthogonals?
I'm sorry?
Since it's orthogonals?
Correct.
Okay.
Correct. That's why lambda 0 has to be, lambda 0, 0 has to be 1. But problem number, look at your notes. Problem 2.9 says what?
Lambda, it's rational if and only if. lambda
It's
zero-
Rotation.
It's a rotation.
It is rotation. So if that is the case, there's nothing to prove. Lambda is already a rotation. So that means you can pick this to be lambda and pick these two to be identity. Identity is a boost with 0 speed. Identity is also a rotation that does nothing. So if that's the case, there's nothing to prove. Okay. Good. So this is no longer 0. Therefore, I'm going to define an ordinary three-dimensional vector. I'm going to call it U1. U1 is the vector, well, I'm going to make a vector out of this. I'm going to divide it. Why am I doing this? Can you guess?
Normal line.
Yeah, you want to make it up?
Normal line.
You're, yeah. And I'm going to call the, I don't want to write down these components all the time. So U1, I'm going to call it alpha 1, alpha 2, alpha 3. That means alpha 1 is this guy over that. Alpha 2 is this guy over that, and so on and so forth. So I want to create a rotation. if I have to create a rotation, I have to find 3 unit vectors. And they have to be orthogonal to each other. That's what a 3-dimensional rotation is made up of. So how do I do? Okay, this is good. This is a good place to start. What do I do with the next? Make them up. So pick any U2, beta 1, beta 2, beta 3, and U3 equals, what did I call it? I didn't call it. I think Neighbor calls this. Gregory Neighbor, I mentioned in the book before. So pick 3 unit vectors such that the first unit vector is constructed out of the original Lorentz matrix. And furthermore, these unit vectors are such that u1.u1 is 0, u1.u1 is 1, u2.u2 is 1, u2.u3 is 1, and u1.u2 is what? 0. We make them orthogonal. We make it like the A, X, Y, Z axis. Okay? Gosh, you have to remember the theorem because I need space. And then I know if I call it not, oh, this is a script R I used to make it 4-dimensional. That's because this is a 4-dimensional matrix, right? So it's sort of a script or a script rotation.
It's just a 4-dimensional R matrix, but it's got
1 and zeros on the the last one. But at the moment, I'm going to define a 3-dimensional rotation. And you guessed it. I'm going to leave a little space, huh? What do I do? Alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, and gamma 1, gamma 2, gamma 3. And guess what? I don't call this R2, I call it R2 inverse. I can call it that if I want. Furthermore, if I take a matrix like this, and if I compute a determinant, it can be plus or minus 1. But I want it to be a rotation, which means the determinant has to be what? Plus 1. So how do I do that? Well, I don't want to mess with alpha. Alpha was chosen for this particular lambda, right? But beta and gamma is arbitrarily chosen. So if I have to, I swap these 2 rows so that this has a determinant 1. Okay, so I assume that that part is done. And then what I'm going to do is construct a 4x4 matrix and then multiply it with lambda and see what it looks like. So my script R, what do you think I do to this? Can I write it like this? I take that 3x3 and stick it in there. And then I start multiplying matrices. I do R1 inverse times lambda. And what do I get? Well, first of all, nothing happens to, we'll see. This is what? 0, 1, 0, 2, I, 0, 3. And I'm going to call this A10 and A20 and A30. Well, I mean, I can call it anything I want, and I don't care about this. I'm just going to call it A11, A11, A12, A13, and fill this part up. I'm not worried about that yet. Immediate questions to ask: how is this preserved? See? I'm gonna have to erase this, but let's do this. 1, 0, 0, 0, 0, 0, 0, R2 inverse, lambda 0, 0, lambda 1, 0, lambda 2, and we'll fill this up as needed. And there's stuff over there. What's the very first entry? It's
And then you should 0 times
this guy.
It'll just give you the first term.
Yeah. And then, what about the second one?
Also, just all zeros except for the first entry.
Is that true? Yeah. Yeah, because I would have lambda 0, 1, and we don't care about the rest of it.
Yeah.
So this row is preserved. What would this element be?
0. Or no, sorry, it'd be whatever the first row is.
So let me write the first
Second
row.
column.
First row, what did we say it was? Alpha 1, alpha 2, alpha 3. So A10, let's just check, is alpha 1 times what?
Lambda 1, 0.
What am I doing here? The very first, lambda 1, 0, plus alpha 2, lambda 2, 0, plus alpha 3, lambda 3, 0. Did I write this any other way? No. But what is this equal to? How was alpha 1, alpha 2, and alpha 3 constructed? I had very cleverly erased it out of the board.
Such that lambda is,
It's same as this.
yeah,
Yeah? So what is this equal to?
lambda 1, 0 squared.
Yeah, lambda 1, 0 squared, and I'm seeing a little typo in my notes. Lambda 2, 0 squared, plus lambda 3, 0 squared, which has to be greater than 0. Because we said it's non-zero, otherwise it's trivial. So we know that this guy,
This is a greater than or greater than and equal to, because it,
oh, sorry,
Yeah,
greater than,
just-
purely greater than. So this guy, very good, this guy has to be greater than 0. That's just parentheses, huh? It's not part of the matrix. We're saying that the first entry has to be greater than 0. Are we good? Okay. Now let's look at the second entry. E20. Because these guys are special, I made it a point to write it down. How do you do that, guys? It's the, so I take the third row, right? And I multiply it with this guy. So this is beta 1, beta 2, beta 3. And so I would get beta 1, lambda 1, 0, plus beta 2, lambda 1, 0, plus 2, 0, beta 3, lambda 3, 0. This is nothing but, what is this vector? This is U2, the vector U2, times the standard dot product of almost U1, but U1 had something in the denominator, so that something was precisely this.
Can you just look at the, actually,
Is that correct? Yeah, because U1 had those things in the denominator, I didn't have that over here. But guess what? U1, U2, and U3 are what? Mutually perpendicular. That's how we picked these guys. So what is U2 dot U1?
0.
0. So to be consistent with my notation, I'm going to do this, and similarly this. these are the 3 facts we have verified about this column. Okay. So, erase all of this. And I'm going to replace this with sigma. You know there are multiple matrix multiplications that we have to do, come up with another rotation. You'll find this almost boring at this point, but we just have to carry it through. I need to come up with another rotation, which means I need to come up with 3 vectors. What do? I pick the following. I pick V2 equals A21, A22, 3. That means this guy I pick to be V2. And V3, what do? This row, I call it V3. Notice, I picked V2 and V3, I haven't defined what V1 is. You guessed it, I'm going to pick, let me call it this. What notation did I use? Yeah, I call it C1, C2, C3. What property must they have? They should be orthogonal to each other. Yeah? Why is this vector and this vector orthogonal and unit vectors? I didn't get to pick these two.
Because U2 and U3 were orthogonal vectors, right? And they're based on
No. Little hidden argument there. This is a Lorentz group element. This is a Lorentz group element. So the product is a Lorentz group element. If you have an element of the Lorentz group, this is a unit vector of length -1. This is a unit vector of length 1, 1, and 1. Except these two guys are 0.
So it has to be.
So these two have to be 1 and 1. Easy to follow. Somebody thunk it up. Yeah? So that is why this just works out. And then as I'm lecturing, I realize I should put more of these details into the written notes. Good. And furthermore, it's my script. I'm skipping the R2. I'm going to call it R2 inverse. And I'm going to have 1, 0, 0, 0, 0, 0. And I'm going to call this row V1. And then obviously V2 and V3, how does it go? Okay, yeah. V2. I'm going to put it this way. And then I'm going to look at R2 inverse. Ooh, what did I do? Yeah, correct. So many matrices around. So I did that. Number 1 inverse, lambda I already did. Now I'm going to multiply by this side. And when I do, I get
Is that last R script too?
script, thank you. You can convince yourself this argument precisely like I did. Knowing that in an element of the Lorentz group, each rows are orthogonal to every other row, and the top row has length -1, the other three lengths are +1, and same is true with columns.
So you're just saying that if you put in the inverse of the other two times the matrix, this lambda right here is the lambda, this is the boost, right? Or is this,
No, I mean, right, so,
this lambda is supposed to be the boost that we had at the
no,
beginning?
no, 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 this lambda is the original lambda given to you.
Okay.
From the original lambda, you multiply it by these two, you get that matrix.
And that's the lambda b beta.
That was one of the homework problem, well, I just mentioned it as a homework problem. So this, by the homework problem that we have technically seen, that you will verify, this is some boost. So then, to solve for lambda, what do? Well, you take this boost and multiply by script R2 here and script R1.
So you have to be given one of the lambdas. If you have one of the lambdas, you can find the
I mean, given any lambda,
you can find rotation matrices.
two
to
rotation
turn
matrices.
into a boost along the x-axis.
Yes. So you have two rotation matrices sandwiched with the boost in the middle. Guys, this is a neat result. Yeah? Because from a mathematical point, this decomposition exists. From a physics point, what are you saying? In my bag of Lorentz group, there's nothing outside of rotations and boosts.
And then if lambda is already a rotation, you don't have to do any of this.
There's nothing to be done. If lambda is already a boost, there's nothing to be. If it's already a boost in the x-axis, there's nothing to be done. So, just for fun, we'll have fun. What we can do is, I give you a boost along the y-axis
Change it to a boost.
and change it to and ask you to find R1 and R2. Good news, rest of the class you can relax. It's fun stuff. Definitions and cool things. Are we good? Take a breath. We define things. That brings the physics of all of this. You can study the Lorentz group till you lose all hair. I think I've done that. But there's so much to it. It's very, very rich. There's a paper written in 1939 by Eugene Wigner. He classified all the Lorentz group, the Lorentz group into all its representations, all its matrix representations. Can matrices of different dimensions represent the Lorentz group? And the answer is you can. And for each representation, a particle that transforms in the representation of the Lorentz group, so it's very important, is a fundamental particle of the universe. And then you go through a list of a few particles, and then quantum mechanics says, well, the rest of them cannot exist. There's a math problem. And you know, since the universe has consulted with mathematics, the universe stopped manufacturing the other particles. I lied, but there's a nice theorem. That's a simple result. This is not, if there's no proof. The statement is the proof almost. So, again, I'm not writing the statement. L is made up of T, remember that T, time reversal, and P, I called it parity, and that's the thing. So really, if you know the Lorentz group, should you care about the inhomogeneous Lorentz transformation, because that was the big papa bear that we started with? Should you care about that? Don't worry, you haven't really missed out on anything. You have your bag of Lorentz group and this parity and time reversal. Let me show you what that how it would read. So I want you to recall, if you will, prove. Recall T was what? Same as eta, right? What's the inverse of eta?
Eta.
And P inverse. So, statement one, if lambda belongs to non-orthogonal, it's very simple. There T P lambda belongs to. Why is that? And why did I need T and P? Because if I just measure multiply by T, I'm going to get an orthogonous, right? Time has been reversed. If this is non-orthogonous, if I multiply by T, I should get orthogonous. Why did I multiply by P? Because this L has a superscript and a subscript. We want the superscript to be correct and the subscript to be correct. What is the subscript? Plus. What does plus mean? Determinant is 1. But T has a determinant of -1. P has a determinant of -1. Because it's minus, minus, minus. 3 minuses. -1 times -1 times 1.
So you have to have parity to make it possible.
To make the determinant possible.
Okay.
So this group is constructed out of these three. I don't want to explain the rest, but suppose I'm concerned with this group. Bring it back to Lorentz. You can find, well, I just told you, time just changes the determinant. And if lambda belongs to L minus, then P lambda belongs to. So no matter where I am, I can multiply with T and P as needed. And get what I want. So this time I promise the hard stuff is over. Let's talk a little bit.
Is T the one that changes the superscript here?
Yeah. So T is this. And P, the space parity is called. It's identity here, but it's -1, -1, -1. So the determinant of this is -1, determinant of this is -1. So if you multiply together, it has determinant 1. It won't change the determinant, but it will reverse the time. This will reverse the time. So if it is non-orthogonous, this will fix it. If it is minus, one of these will fix it.
And that's what changes the superscript? with C.
So what we want to do, yeah, we multiply by parity because this is already orthogonal. We don't want to change the direction of time.
Okay.
We just want to change the determinant.
T changes both, P only changes determinant.
T changes both, P only changes the determinant. Good. Good. So, A, we have figured out what the Lorentz group is made of. It is two rotations in the boost. We did have, not that we would particularly care, we did have the general homogeneous Lorentz transformation. Okay, that's too many things to keep up with. What is that made of? Well, Lorentz group and T and P. Just to label your bags properly. You know, when you put books in a closet, you want to identify which is which so that you can retrieve it as needed. That's what we have done.
The general group is just L.
Correct. Yeah, that the L is all the stuff that, you know, our fundamental, that is L. This preserves the inner product, but it could reverse time, it could reverse orientation, that kind of stuff. Yes, sorry, I go. Should it go up? Huh, what was that?
No, you said, well, it does make a lot of sense, and I said, this part, yeah.
Yeah, it's all of it makes sense. You just have to go over it over and over. No.
Yeah,
You know what I mean?
eventually it does
You have
make
to
sense.
just let it sink. If I'm studying a new result, if I'm reading a new paper, I can understand the plot as I go along. But if I want to make a result that is important, that is part of me, I have to revisit it multiple times. All of you will have to do that. Did I promise some nice definitions to relax?
Nice definitions of positive.
To
No, like you know, like
Yes,
on
I know.
YouTube at night. Exactly.
yeah, that's it. What did you call it?
Like on YouTube, they have these videos like
Relaxing music.
relaxing music, fall asleep to.
Or
Yeah,
like just
yeah.
relaxing nails on chalkboard.
No, I mean, gosh, you guys deserve it. You know, I feel like that. I periodically abuse you in class, so.
You shouldn't say that on camera.
Oh, well. I think at this point I've said too many things on camera that I shouldn't say. But, yeah, and I've moved these definitions around so it reappears. In the notes, it's a final clean version, I suppose. And so I'm just, if nothing else, we are reiterating, you know, the C, T, X, Y, Z, along with the inner product eta, is what I'm referring to as Minkowski spacetime, and it's a four-dimensional spacetime. So I'll again use my script. I don't know, guys. It's hard for me to come in this font.
Looks like a spider. It's good.
Yeah,
It's an M for Minkowski, and I put a 4 on top. But this is the only time I'm going to do it. Very soon it's going to be M4.
And you're saying that these are all within M4?
By M4, Minkowski spacetime, I mean a 4-tuple, set of 4 numbers, along with this inner product.
So is the Lorentz group within Minkowski space?
Yes, Lorentz group acts on Minkowski space
Oh, okay.
because it is something that preserves this object that is part of the Minkowski space. Yeah. Definition 2.9. So if I take the set lambda A, here lambda belongs to the Lorentz group. And A belongs to any point in Minkowski space. It's a 4-dimensional translation. Yeah? This collection also has incredible mathematical property because it's a pair of things. This is a matrix, this is a set of 4 numbers, right? So, this is, pairing things that are not related, So it has its own interesting mathematical structure. This is called the Poincaré group. And there's that. This is called the Poincaré group. And under the Poincaré group, a vector transforms like so. Questions? Make sure you understand that. So now I'm going to look at any x in M4. Yeah, I can do that. I can do like one line. Because pretty soon we have, in general relativity, manifolds that are 4-dimensional. It could be a 4-dimensional torus and whatnot. It's bad if the universe is a 4-dimensional torus because we'll have time-like loops. Terminators will surely exist. So let me draw this. This is the point x. It's a 4-dimensional space. But then at x, I'm going to consider the set of all vectors. You could consider this vector, all of them. The set of all vectors, at x in M is called the tangent space. At x, and is denoted as the tangent space at the point x of the geometric object, that is the Minkowski space. Yeah, just a definition. Next, I want to define a vector field. What do you think a vector field is? At every point it is a vector. I just want to clarify because we'll be using these things. Definition 2.11. So a vector field y in M4 is such that if I evaluate y at the point x, this belongs to the tangent So if I were to graph a vector field, and this will be the last thing to do. So this will be a vector field. Such that at any point x, this is my y x. It's a tangent at that point x. Correct? And I don't want my vector fields to be choppy. Meaning all of a sudden, right next to it, I don't want it to go like that. I want it to nicely flow like water. So what do I require? I want, the components of these guys to be nicely differentiable. That means this should exist for all values of nu. What, t, x, y, and z. It should be nicely differentiable. We won't have to worry about this because if we can differentiate in this course, can't do much with it. There's sine functions, cosine functions, sinh functions. You don't want complicated functions, step functions. You don't want that, right? The vector field was 0. All of a sudden, you snap and it comes out. That is artificial. Okay. Happy Friday, all.